Hi, Mick McQuaid here, welcoming you to day 6 of iste780, Data-Driven Knowledge Discovery. And today the main thing we're going to do is a lab. But first I'd like to talk about an extended example of multiple linear regression, and then something that's not on the menu here, but which we need to talk about, which is a comparison of linear regression to k-nearest neighbors regression. Then the rest of the time will be devoted to this lab. We'll go through libraries, simple linear regression, multiple linear regression, interaction terms, quadratic terms, qualitative terms, and we'll write a short function. And then hopefully you'll get your homework done and turned in Roman numeral 2, exercise 379. Okay, let's get started. So the first thing to talk about throughout chapter 3, we've been talking about the sales and advertising data. And so this revisits that data, this section revisits that data and gives an idea of how you would answer questions such as you get in the homework. Is there a relationship? How strong is the relationship? Which media contribute to sales? And it basically relates the techniques, for example, the p-values or the r-squared statistic or the t statistics associated with the betas, and so on, the confidence intervals here. And so you should take this as a guideline, but you don't need to be as verbose as this. This, in addition to giving you the rationale for the answers, this also calls attention to the section and all that kind of stuff. I'm not interested in all of that. What chapter all this stuff happens in, what table that it all happens in. I'm interested in you giving the techniques that you use to get it, and then making the fairly brief statement like the p-values for TV and radio are low, but the p-value for newspaper is not, and so on. Now, some of the items that are in here we'll actually go over how to determine them using R today. So there are things like, for example, collinearity we've talked about, but you haven't known how to calculate it, so we're going to deal with being able to calculate that today. We'll deal with prediction. I don't think we've dealt with how to calculate a prediction interval so far in R. We have dealt with some of this stuff already, so some of this stuff should be very simple. Okay, now k-nearest neighbors regression is like k-nearest neighbors classification. We do a regression based on the k. We choose a value of k, and we find the k nearest neighbors, and we get, basically a result that corresponds very much to the value of k that we chose. So here's k equals 1 and k equals 9, and you can see that k equals 9 is a much smoother fit. And having a smoother fit suggests less flexibility in the model, and that suggests less variance in the model, but it also suggests higher bias in the model. And that's one of the key points that we take away from this section. And there are some examples here. This is just telling you how it's constructed. And this set n naught is the k training observations that are closest to x naught. And the big issue here is the bias-variance trade-off that we've talked about before. And we want to make sure that we're aware of this. There are going to be some times, and we're going to look at some pictures in a second here, there are going to be some times when we want to go one way or the other in this trade-off. And there are some times when we want to skip this method entirely and use a parametric method instead. So remember that being a non-parametric method has the problem that we can't really explain what's going on. We can't interpret what's going on in the model. So here's an example of k-nearest neighbor on a data set that is actually linear. And with k equals 1, we get this highly flexible, way too flexible fit that probably has low bias and extremely high variance. The true nature is hidden in here somewhere, but it's too variable around that. So when we do k equals 9, we get much lower variance. We potentially introduce some bias, but in this case we don't introduce significant bias because it happens that the nature of the true nature of the function that generates the data is pretty easy for this to coalesce around. And unfortunately, though, for k nearest neighbors, we're going to see that if it's easy for k nearest neighbors to coalesce around it, it's even easier for linear regression to coalesce around it. So here we see the same thing. The true data, I think, is the black line, and that's the true data. And then and remember, this many of these examples use cooked data. So this is a simulated data set just to prove a point. In real life, we don't know the true nature of the data usually. Sometimes we have so much data that it's hard to argue with, but in general, we don't care about situations like that. Those are already what we would consider solved problems. But this is just to make a point. So the dashed line here, and let me just zoom in on it. The dashed line here represents the least squares line, and the least squares line you can see is very close to the real thing. And over here on the right side, we see sorry about that. We see the mean square error plotted against 1 over k. Now, the mean square error for the least squares regression doesn't change at all. This is the mean square error for least squares, the least squares line, and it's a constant. And it's better. Remember that we want to, the best function that we can get is the function that minimizes MSE. So the k nearest neighbors that minimizes it is going to be one with a very large k, because with a very large k we're going to be close to one. Excuse me, what am I saying? A very this is 1 over k. So this is a very small k, right? A very small k is going to be, no, a very small k, oh gosh. So this ranges between a very small number if k is large and 1 if k is small. So we want a large k here. Sorry about that, I'm misreading this plot. So we want a very small k here. But even if we have, did it again. So we want a very small value of 1 over k. Which is a very large value of k, right? Gosh, I'm really out of it today. Okay, so even when we get to a very large value of k leading to a very small value of 1 over k, we're still in trouble compared to least squares regression. Least squares regression does a better job for us across the board. But that's in the case of a data set that is generated from a genuinely linear function. Let's take a look at what happens when a little bit of non-linearity is introduced, and then we'll also look at what happens when a lot of non-linearity is introduced. So first, let's take a look at a little bit of non-linearity, and what we find out here is that these are two different. Let me be reminded what this is. Oh yeah, k equals 1 and k equals 9. So the blue is k equals 1, and the red is k equals 9. So here again, we get the smaller k is, the more flexible the line is, and as we grow to k equals 9, the function is less flexible, but in this case, it happens to be a better fit to the true value of the function. We're not seeing the points in this particular case. So what happens is that with very large values of k, some of those values are superior to linear regression, and as we get smaller and smaller values of k, leading to larger and larger values of 1 over k, the MSE gets worse and worse. But the best that we can do is to use k nearest neighbors in this case. One of these points here must be the lowest. So this area right here, we can do better using k nearest neighbors than the best that we can do with linear regression. Now, I'm guessing, the function isn't shown here, but I'm guessing that if we added a quadratic term to the linear regression, the problem here is that we don't know the true shape of the data, but if we have enough training data to make a guess, then I would imagine that least squares regression can be made to perform better with such a simple curve. We've seen that before. But with a more pronounced curve, we had a tough time when we added some higher order terms in least squares. And here, least squares does badly across the board. K nearest neighbors, no matter what, is better. And here again, we see it's performing substantially better with larger values of k, meaning smaller values of 1 over k, and gets worse and worse. But still, the worst that we can do with this, no matter how stupid we are, no matter how badly we choose k, we're still better in this. If this is the actual shape, which in real life we generally don't know, if this is the shape, then we're better off with k nearest neighbors. Now let's look at another example. Here's a case where linear regression performance deteriorates a little bit. I don't think you can even see it on this. Oh, okay, I guess you could just sort of barely see it on here. But if we increase the dimensionality, so here we're increasing p, and if you look very closely, I think you might even have to put a ruler over it. This line is getting slightly, just very, very slightly higher. But the performance of k nearest neighbors on mean squared error just really collapses under the weight of dimensionality, under the curse of dimensionality. And this is a point that's made extensively in the text, that we often suffer from the curse of dimensionality when we use k nearest neighbors because there are no neighbors. Once we get into high dimensions, no point has any neighbors that are even remotely close. So in the case of high dimensionality, and this afflicts non-parametric methods. So in general, if we have high dimensionality, we expect parametric methods to perform better than non-parametric methods because of the curse of dimensionality. Now there are a few other points here that I have sort of skipped over just by highlighting the diagrams. One is the interpretability standpoint. So I think I've already made that point repeatedly, that linear regression is one of the more interpretable models. KNN is among the least interpretable models. I think there are a few other points here that I may have glossed over. Let me just take a glance at these. You should certainly read this over. My lectures here are really just to hit the high points of the text, but the text is quite valuable. And there are some points where I don't agree with the text, but for a class like this, I don't think that that's particularly important. Sometimes I can identify other texts that will contradict this text, but I don't think that that's important. You have to know that there is a lot of controversy in science, and the more you learn about science, the less you'll know, because the more you'll be exposed to the notion that some of these ideas are controversial. Okay, so the rest of the time I want to spend on the lab, so let me take this out of the way here. And I've got my text editor already open here, and the first few things that I want to type in are already here. So let me turn on R, and it's off the screen here as usual. So I'm going to put it over here and try to shrink it down a bit. And these are just a couple of options that I like to give at the beginning. Oops. To make it more tractable. And then the beginning of the lab asks us to load a couple of libraries. Now, the first library I can load without incident. The second library, oh, you know what? I have actually installed. So the second library is not installed by default. Ordinarily, let me just put in a fake. I'll say library blah. I doubt that there's a library called blah. So this is the kind of error message that you should get the first time that you try to load the library ISLR. So I'm going to go to the package manager of my graphical version of R, which I can't seem to find. There we go. And this is a package installer. If I'm using the graphical version of R, one of the menu choices will be a package installer. There's also a package manager. But opening the package installer here gives me a list of potential packages, and I can search. You can see here I've already searched for ISLR, and you can see that ISLR is already installed, and that the version of it in the CRAN, the Comprehensive R Archive Network repository is the same version that I have. So if in fact I didn't have this, I would click this Install Selected button. Now, there's one thing that I have to tell you that's very important about this using this interface. This is not checked by default. This is left blank by default, and all you'll get is error messages all the time if you leave this. I don't know why they don't make this the default. This obviously should be the default. Install dependencies. Now, it happens that ISLR doesn't have any dependencies, so it isn't going to matter in this particular case. But in most cases, most packages depend on, most of the packages that you actually want to use depend on base packages, kind of upstream packages that are not meant for the end user, but that are meant for other packages to be built upon. So it is the general rule that there will be dependencies, and so you have to click this Install Dependencies. Now, if you do not have a graphical interface to R, you can still do this by using the install.packages function. But I find the graphical one is easier to navigate, and if I want to find other things, I can. So, and we'll do that later. We'll find another package later. But as it turns out, I happen to already have this installed, so I'm going to just use it. Okay, and then what we're going to do is use a data set called Boston, and it is about housing values in Boston, and I'm just going to find out what the names of the columns are in the Boston example, in the Boston data set. And the main ones that we're going to deal with immediately are MEDV, that's the median value of a house, and LSTAT is low socioeconomic status. So is the house in a neighborhood that is predominantly low socioeconomic status? And so we're going to do several regressions with that. And then there are various other things here, like RM is the number of rooms in the house, the age of the house, average age of houses in that neighborhood, and some other stuff that will, some of which we'll deal with, some of which we won't. So we're just going to do a few simple regressions here. And the first one is going to be median value as the response and LSTAT as the predictor. So that's a simple linear regression with one variable. Now, this function generates an object, and so we want to save that object. So we're going to say lm.fit, and that object is going to get the value of this function. Okay, so I do that, and I get an error message. Oh, because I haven't attached this. So I can do one of two things. I can either do what they do here, which is say data equals Boston. So if I do that, it now works. Or I can say, and what I usually prefer to do, because I usually am only working with one data set at a time, I'll say attach Boston. And now I can do it this way. And I get the same result either way. Okay, now if I just mention the name of this object, lm.fit, I get a few items. Okay, I get the beta naught and beta 1, the coefficients of the model. Call that the model is y equals beta naught plus beta 1 times x plus epsilon. And in this case, beta 1 is negative. The slope is negative. So beta naught is the y-intercept, and it says intercept there. And the coefficient for low socioeconomic status is negative, which suggests that the median value decreases as the percentage of low socioeconomic status increases, which is not a particularly surprising result. Okay, now if we want to get more information, we can say summary lm.fit, and this gives us a standard summary of the object, which is a summary of the model. This is a linear model. LM stands for linear model. And there's also GLM, a general linear model. Okay, and we can see from this that we have an R squared of a little over 50%. The p-values are exceptionally small for both beta naught and beta 1. We already know this. Oh no, have we dealt with this data set? I can't even remember now if we've dealt with this data set. But in any event, this model explains perhaps half the variability in the data. So that's a pretty good model as it stands. What are the other pieces of information that are available to us? We can say names lm.fit, and this will tell us what other things are available in this linear model object for us to play around with. One is the coefficients, which is what we got initially. So we'll just do that, coef lm.fit. And in general with R, I should point out that as soon as something is unique, as soon as you might not mean anything else, you can. Well, no, that wouldn't be the case for this. Never mind. Forget what I was going to say. Confidence intervals are available here. And by default, this is going to give us a 95%. Yeah, 95% confidence interval. We can also get prediction intervals. So I'm going to say predict, but first I'm going to say, let's see, I'm going to give an LSTAT value that we want to predict from, or actually a vector of values that we want to predict from. And we're going to look at the confidence interval, and then after that we'll look at the prediction interval. Okay, and so there were three values of LSTAT, so we've got three predictions: the fitted value, the lower bound, and the upper bound. Let's do the same thing, but with the prediction interval instead. Is it predict or prediction? Let me see. Prediction. Okay, and you can see that the prediction interval is wider than the confidence interval because the prediction interval has to take into account the variability not only of the mean but of all of the data. Okay, and we can also plot these. Let's plot LSTAT by median value. And this went off the screen, so I'm just going to drag it back over here. And you can see that there is this negative relationship between these two variables. And I can also put an AB line through this. And there's the AB line. And I can also make the AB line more prominent. So here are a couple of things that I can do. I can make it more prominent by widening it. That's the first thing I'm going to do. Then this is going to make it 3 times as wide. And then I can change its color. This is going to make its color a hideous shade of red. And when I say hideous, I mean only from the psychological standpoint. So we'll talk more about that later. Let's see, I want to plot, oops. Oh, I want to plot LSTAT and MEDV. So again, this is low socioeconomic status by median value, and this will be with the color red. Oh, there's no such thing as plot L, of course. Okay, there it is, plotted with red. Now I can also change, in addition to changing the color, I can actually change what kinds of plotting characters are used. So the plotting character is abbreviated PCH, and what we have been using up until now is a little circle, and there are 20 different characters that we can use. Plotting character number 20 is a dot, and I can also specify a character. I don't have to specify it by number. I can specify a plus sign as the plotting character. Oops, I forgot to leave the one that I had there. What was this? That was number 20, I think, right? Yeah. Okay, and then I can also, if I want to just see what plotting characters are available, I'm going to plot from 1 to 20, 1 to 20, PCH equals 1 to 20. And now I'm just going to get a diagonal row of plotting characters. And these are the plotting characters I can use. And you can see that by default we've been using plotting character number 1, which is the circle in the lower left-hand corner, and the dot is in the upper right-hand corner. And it's frequently the case that you'll want to use a series of plotting characters instead of an individual plotting character. And R has good rules for doing that kind of stuff. Okay, now the diagnostic plots, which we've already done, but we're going to do again, that come by default from the linear model object are going to be seen here. This sets up a 2x2 panel, and this is going to plot LM fit, which by default is going to have 4 graphics. And unfortunately, it's really hard to see the graphics when they're this small, and if I enlarge them, it's going to go off the screen here. So let us, you do this also, and you enlarge it to the maximum that you can fit on your screen, or you can just do them one at a time. So we can do stuff one at a time here. I think I might be in a situation here. What is this? Compute the residuals, blah, 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 predict LM fit. I think I'm going to actually still be in this panel setup. Yeah, I'm still in this panel setup. And I can do studentized. This is a form of standardization. And I remain in the panel. And I can also plot the hat values. So if you recall, these are the values that indicate whether we have high leverage. And I can also go back to, I can also find out which is the largest hat value. It's actually probably shown on this plot, it's just that it's too tiny for you to see. The plot hat values, I think, identifies the largest value, or values, according to some complicated rules. But I have to go back to the other display to show this. This is just going to return a number. So the largest is 375. And it's interesting, 375 appears here twice. I would guess that means that there's nothing even close to 375. Because when I've used this, it'll generally plot the 2 largest values. Okay, now, so that's it for simple linear regression. So now the lab moves on to multiple linear regression. So I'm just going to put a comment character there. And I'm going to create another linear model fit object. And this one's going to have, again, we want to know the median, the output is what is the median value of the houses in the area. And we're going to make a model based on low socioeconomic status and the average age of houses in the neighborhood. And the summary of this. And just at a glance, this doesn't look, significantly better than the other model that we just did of LSTAT alone. So it still does predict. Doesn't look like there's anything particularly wrong with age, but it's just not helping much. What if we want to just do them all? I think that's the next thing to try. Yeah, let's just do them all. So I'm going to change this a little bit. And this is one where I have, even though I have already attached Boston, I still have to say data Boston if I'm going to use this notation, I think. Okay, and now the summary of this is quite a bit more extensive. There's, oops. No, it's not that much. It's not that much longer. It's just this long list of variables, and you can see at a glance that a couple of these variables are pitifully useless. So if you take a look at this column right here, these are the p-values. And if you just eyeball it, you can see that age has a terrible p-value, and indus, whatever that means, has a terrible p-value. But we're getting a better R-squared, so this is explaining more of the variability, although at the cost of just throwing in a huge number of variables. I would prefer the most, so in general, we prefer the most parsimonious of models that have roughly the same explanatory power. We would like the most parsimonious model. It's a sort of general rule of all kinds of scientific measurement. Okay, and we can do the variance inflation factor now. Now here is the case where I am going to point out that you really need. So I've already installed the car so you have to install the car library, and this took me a long time. I have a slow network connection right now, and the problem with this is that it has about 10 dependencies. So when I chose this and I installed it. It took a long time, and here for the graphical version of R that I have, here's how it looks. These are each one of these little sections here refers to so the car was the last one. The one before that was survey. The one before that was sparse matrix. The one before that was sandwich. The one before that was matrix models. The one before that was kitchen sink. No, I'm just kidding, and so on. So there are lots and lots of things to load before car gets loaded. So let's now use the car library. Oops. Library car. So get that installed and then restart the video at that point. And why did I not get anything here? This isn't working. What am I doing wrong? Something bad just happened, I think. I think I just lost the connection between my, what the heck is going on here? Wow, okay, so that was pretty weird. I was in, I know what happened. I was in a special cut and paste mode in this window. That was the problem. I forgot I was in that mode, so it was holding off on sticking my results from the editor in there. Okay, so anyway, we did VIF, and we find, most of the VIFs are not too bad, but some of them, like tax and rad, whatever rad is, are pretty high. Yeah, so I would say there's not much risk of collinearity except with rad and tax. Those are the Those are the ones to be concerned about here. Okay, so now let's do a regression of all of them except, so we're going to do the same thing again, except we're going to get rid of age. So this notation, saying minus age here, is going to do the same thing, except without age. And then if we do the summary of this, it looks very similar. The model hasn't gotten any worse from removing this one variable. And I'm basically, reason I'm saying that, I'm basically just eyeballing the r squared and adjusted r squared really quickly. Now, another way that we could do this is the update function. So instead of doing what we just did, we could say lm dot, oops, wait a second. Let me do this again. I see that the way the lab is doing it, I was meant to do this. Okay, so let me do it this way. lmfit1 gets update lm.fit tilde dot minus age. And this syntax seems obscure now, but once you're practicing it for a while, I promise it'll get easier. Okay, and so now I have this, I have basically what I just had. I'm not going to do it again. Okay, now let's talk interaction terms. So here is, so I'm just going to put a comment character in between there. In fact, let me just go back and say enter. And this is multiple linear regression, just in case I want to go back and look at this. Or if you want to look at it, you want to compare what you're doing to what I'm doing, see if there are any differences in spelling. Okay, now what I'm doing here is actually more than what it might look like. So I'm saying take the product of LSTAT and age, but also take LSTAT and age. This is shorthand. The asterisk is shorthand for three things. I want LSTAT, I want age, and I want the product of them. And so that's what we've got. And if you recall, the r squared is about what it was before. Very slightly improved over what we had before, I think. Well, I mean, when we just did LSTAT and age independently. The product of LSTAT and age is denoted LSTAT colon age. And so you can see over here that we have this LSTAT colon age here. And it has significance even though age doesn't. These asterisks, by the way, refer to these p-values right here. So the fact that there's no asterisk here says that this p-value is insignificant, which you can also tell by looking at the p-value, that this is significant at the 0.05 level. And if we have more asterisks, it's significant at a level. This one, three stars, indicate that it's at the limit that this computer can resolve to. So 2 times 10 to the minus 16th is the limit of the smallest number that we can represent in this particular implementation of R in this particular computer. Alrighty then. So so we've done that interaction term. Oh, now let's try a quadratic term. So the next thing is going to be, I'm going to say quadratic term. And what I'm going to do is create a new lmfit object. And this one, oops, I'm all thumbs here. And this one is going to be median value times LSTAT plus LSTAT squared. Now, in order to get LSTAT squared, oops, LSTAT, can't talk and type either. in order to get LSTAT squared, I have to wrap them in this I function, this ignore function, because otherwise the caret symbol is going to be interpreted as something else. So hopefully I spelled that reasonably well. And summary of LMFit2 is going to reveal that this is way better than LSTAT. If you recall, the R squared for LSTAT was around 54 or something. And so we are explaining 10% more of the variability by adding in the quadratic term. And I think, and it also has a small p-value that's also mentioned in the lab. Now let's do this. Let's compare. So this is a really good exercise. This is an important thing to do. We want to compare the more extensive model with the reduced model, and the reduced model will just be LSTAT by itself. Okay, so I don't remember what LMFit was the last time we looked at it. But now we're going to do an ANOVA of LMFit versus LMFit2. And this is telling us that, so this is measuring, or I should say it's comparing the hypothesis that the two models fit equally well. That's the null hypothesis. And the alternative hypothesis is that the full model is superior to the partial model, model 2. And this measure of the p-value for the F statistic, so this is an F statistic for that, and this is the p-value for the F statistic, and its significance tells us that indeed the full model containing the quadratic term is clearly superior. And if you recall from a couple of days ago, we looked at this sort of saddle-looking picture of the model, the linear model fit, that suggested that something nonlinear was going on. And in fact, this is sort of the numerical justification for what we first sort of thought we saw in a picture, and now we have a clear numerical evidence for it. Okay, and then we can also look at this. Unfortunately, this doesn't look too great on my display. I already have looked at this LMFit2. So I'm just going to do this. And you can't really see it very well here, but there is no pattern to the residuals here. And it would be good if you can on your display enlarge it. I'll just briefly enlarge it here. And this is a good-looking set of residuals. This is telling me that we have extracted a lot of the pattern that's in the data, a lot of the variability that's left. Now there's still, over 30% of the variability remaining, but that percent of the variability that's remaining doesn't have a pattern to it. That's what's significant. Okay, and that. Oh, and also it's suggested that so I guess we'll just say, we'll call this polynomial terms, because now what we're going to do is get all the terms up to the 5th degree. And the book gets pretty excited about this. I'm not, but it's arguable, I think. I think it's an awful lot of terms for very little gain, but there are situations where that's make or break, where being able to explain something with a lot of terms, being able to explain some variability with a lot of terms is extremely useful. So this takes us up to 67% of the variability being explained. And the book points out that they also tried it with higher degree terms and didn't get any improvement. You can see all the p-values for p-values for each term are significant. They're not significant for any degree above 5th. Okay, and then we can also do a, let's see, what is this? We can also take the log of a variable instead of a quadratic term. And see what happens. And I did not type in enough parentheses, I think. Is that right? I'm just going to go over here and type in one parenthesis and see what happens. Okay, yeah, that's what happened. Okay, so the log of number of rooms turns out to explain 43% of the variability. So, yay! Yay for the logs of terms. So a lot of times that's going to be significant. Here, I don't think it's particularly significant. But if you want to investigate that further, what would be the next thing you would do? I mean, the next thing I would do is just take this log away and see what just rooms by itself does, and see if transforming rooms is actually better than rooms as a linear term. Okay, qualitative predictors is our next trick. And we're going to use the car seats data, which is part of the ISLR package. And so this is sales of children's car seats. So that's the very first item there, sales of children's car seats, and a bunch of other information about the sales of car seats. So we're going to see if we can predict sales of car seats based on some other predictor. And one of these predictors is in particular this one right here. Shelving location is a qualitative predictor. It has 3 values: bad, medium, and good. And what's happened here, or what's going to happen here in a second, is that R is going to automatically set up a qualitative, an indicator variable, or dummy variable, as the book likes to call it. So we're going to do a couple of interaction terms. Now notice the way that we're doing these, if we spell them correctly anyway. The way that we're doing these is we're not including the underlying terms. And if you recall, the book suggested that we typically want to include the underlying terms. Okay, so we're doing, let's see, so we're doing sales by income times advertising and price times age. That looks right to me. I don't think I've misspelled anything. Let's see what R thinks of it. Oh, R seems to like it. Okay, let's look at a summary of it. So recall that before, when we did the interaction terms, we said income asterisk advertising, or the equivalent thereof, which would have left income and advertising in, as well as the interaction term. Oh, we did everything. I'm sorry. We did. No wonder we didn't. No wonder we did it this way. So the dot meant do everything plus these interaction terms. Okay, and there is actually a shelf location good and a shelf location medium. I guess that should be shelf location good and shelf location medium. And so this is actually a this is a variable. Shelf location good is a variable that takes on a 1 if shelf location is good and 0 otherwise. And shelf location medium takes on a 1 if shelf location is medium and a 0 otherwise. And if shelf location is bad, then the intercept is our predictor. Okay, so that's how that works. And R's done it essentially automatically. We just have to know how to read it. And we can look at it. Oh, here's how we can look at those variables. Contrasts. Okay, and you can see that I did not bother to attach car seats before, but I have now. And so now we see that good takes on a value of 1 in the case that shelf location is good. Medium takes on a value of 1 in the case of shelf location being medium, and they're 0 otherwise. Okay, and that's it for qualitative predictors. Now the next point and the last point is libraries, right? Or excuse me, libraries is writing functions. So we can write our own functions. So let's see if there is a function called load libraries. Okay, whew, there isn't. I was afraid I had already created it earlier. So the object load libraries is not found. Let me try it as a function. Could not find function load libraries. Okay, so let's create a function called load libraries. So I'm going to say load libraries gets function with the following stuff in it. Library ISLR, and of course you have to have already have to have installed. So I should mention here that with R you can have a lot of stuff installed, but it's not in the current environment. So you have to both install something one time, and then whenever you want to use it, you have to, in your current R session, you have to say library and then that name. Although you can automate that if you're always using the same libraries. Okay, so now I have this function, and all it does is load this library, and then print out the message the libraries have been loaded. So let me, I'm just going to do it one at a time, as it would be if you're just typing it into the R interface. You'll see the same thing that the book mentions, which is that you have a little plus sign here now, because R knows that it hasn't reached the end yet. And only when I type the closing curly brace will R think that it's ended. Okay, now I can go back and say load libraries, and it's going to tell me what load libraries is. So that's actually what happens if you call a function without the parentheses after it. It just tells you what the function is. If I want to actually call the function, I have to include the parentheses. So if I call the function, it's actually going to load those libraries. Now those libraries are already loaded, but it's just loading them again. So I could put this in my R initialization file, R profile, or whatever I use for initialization. R has a lot of has a good system for letting you have a system-wide initialization, a session-wide initialization, and then a project-wide initialization. So you can use function, a function like this is potentially useful. And then there are all sorts of functions that you'll add for yourself. For example, I have in another place, I have these two functions in a system-wide profile. I've suspended using that for the purposes of this class. I do have a system profile that, for example, causes this to be in stuff to be in color. That's just loaded automatically. Okay, so that's it for the lab. Now the next thing is the exercises, and it's worthwhile to do more than the exercise to turn in. There's only a certain amount of exercises that I can look through and grade in a very short time before our next class. So I do encourage you to do more of the exercises, and the solutions to the exercises are online, so it should be possible to get feedback on the other exercises. And I'm happy to try to give more feedback, but my first priority, of course, is to keep the class running. So thanks for your attention, and good luck with Elmo.